Hey guys, it's Mr. Lowry. Welcome to week 2 of quarantine lessons. So I'm not really allowed to come to school anymore. I mean, I can if I have to, but I'm pretty much supposed to stay at home. So this video is coming to you from an undisclosed basement somewhere. This is my basement setup, so hope you enjoy, hope you can see okay. Today we're going to talk a little bit about properties of quality and properties of congruence again, just to kind of like refresh. And we're going to do a few more segment proofs like we did last Friday. Proofs can be a little bit tricky, and so my strategy for helping you guys learn proofs is to just walk you through a bunch of them and then just have you kind of like copy those proofs over. If you feel like you can do some of these proofs on your own without coming back and watching a video, great, that's awesome. For some of you guys that might, have a little bit of difficulty kind of figuring out, well, what is a proof and how does it work? I want to be able to kind of walk you through that and help you out. You're going to cover proofs again next year in SM2. This is kind of an intro, and so if it's still a little bit foggy at the end, don't worry too much. You'll see it again. But I just wanted to give us kind of another day to practice some of these segment proofs before we move on to angle proofs. Which we're going to do. So we're actually starting, we're doing 2-column proofs, we're proving some new things. We're going to prove a couple theorems this week, and today we're actually going to prove a few properties, which is cool. So before we just were like writing down definitions, we were writing down postulates. Now we're actually getting to the point where we can use, our deductive reasoning and definitions that we have to actually prove some stuff. So let's go through properties of equality and properties of congruence again a little bit. Okay. And we're going to we're going to focus on how properties of equality and congruence look in terms of segments, line segments. We're going to kind of do the same thing again later this week with angles, and we'll kind of do the same kind of idea, but with angle measurements. Today we want to focus on segments. So these are 3 properties of equality. Obviously they're not all of them because we have the addition and subtraction property, and we have the multiplication and division property, we have the substitution property of equality. But these are 3 that are in common with the properties of congruence, okay? Euclid would probably call these common notions because they're pretty obvious, right? Reflexive property is that just anything is equal to each other. That reflexive property of equality, anything is equal to itself, right? So here are a couple examples. 5 is equal to 5, okay, pretty obvious. X is equal to X, okay. Now this is like a segment measurement. So remember when we see 2 letters together, those represents the segment that connects 2 points. And actually, it's not just the segment that it represents, it's the measurement of between those 2 points. If we were to write a line on top, that would represent the segment that connects AB with just AB next to each other. We're talking about the measurement of segment AB, which is really just a number, right? Maybe 5 centimeters or 6 inches or whatever. So this is just some measurement equals itself. Okay, pretty obvious. Symmetric property is basically that if you have an equality statement, you can switch the sides and it doesn't matter. Equality is saying 2 things are equal, so whether one's on the left and one's on the right, they're still equal. So if x equals 2, then 2 equals x, right? That's a statement that you can switch backwards. And here's how you would see it with segment measurements. If a segment measurement AB is equal to some other segment measurement CD, well then you could just reverse that statement and it's still true. So this is how the symmetric property of equality would look if we're just talking about segment measurements. Okay, here's transitive property. It basically says if A equals B and B equals C, whoops, the last statement should be here then, that A equals C. So let's add that. So if we got one thing equal to something, and then that thing that's equal to is also equal to something else, we can kind of jump over the B's and just say the first thing has to equal the last thing. If you remember when we were talking about like statements and deductive reasoning, that's kind of what we call the law of syllogism, right? If P implies Q and Q implies R, then P implies R. We can kind of skip the middle statement. This is kind of a just similar thing, just with like segment measurements. So if some segment measurement AB, which would just be like a number, equals some segment measurement CD, and then that segment measurement CD equaled another segment measurement EF, then the first segment measurement AB would have to equal the last segment measurement EF. Okay, so that's just those properties for equality in terms of segment addition, or segment measurement, excuse me. Now, the idea is properties of congruence, we still have those same properties with congruence. So, any segment is congruent to itself. Now, we're not talking about numbers anymore, we're talking about a shape, a segment, like a shape, So any segment is congruent to itself, right? Symmetric, so you can switch a congruent statement if you're talking about segments. So if this segment is congruent to this segment, you can reverse the order and it still means the same thing, right? AB segment is congruent to the CD segment. Cool, then the CD segment is also congruent to the AB segment. Those statements are equivalent, we can do that. Okay, and the transitive property. If one segment is congruent to a second, and that second segment is congruent to a third, well then the first segment and the third segment have to be congruent to each other. Let's make this a segment. Okay, now those seem pretty obvious. These properties of equality are probably what Euclid would call common notions. So things that are pretty obvious. He would say something like, for like transitive or something like that, two things that are equal to the same thing are also equal to each other. He would call that a common notion. Now these properties of congruence are kind of similar, where you're like, yeah, that makes sense. That kind of, if two things are congruent and the second and third thing are congruent, then the first and the third. Those are all, pretty obvious, but we can actually go improve these. So I think that it's a good exercise to go improve this, just so you can kind of see what deductive logic or deductive reasoning looks like. We could say these are common notions and just use that as part of our axiomatic system and say, well, these are pretty obvious, so whatever. And they kind of are, but I want to show you, just so we can practice, how to get a property of congruence from a property of equality. And then once we do this once and for all, we can just use these properties of congruence without really thinking about it. So remember that our bridge between equality and congruence is the definition of congruence. Now specifically here, we're talking about the definition of congruent segments, which means the segments have the same measurement. So we're going to use, in a couple proofs, we're going to use the definition of congruence. And remember, I kind of abbreviate that as def of Cong. Now this is specifically, we're talking about segments today, congruent segments. Right? But congruence kind of means the same thing all the time. It means equal in measurement. So congruent segments have the same measurement, or they're the same length, or the distance between the endpoints are the same. So that's kind of what we're going to use here. Def of Cong, or the definition of congruence, is our bridge between equality and congruence. So we can kind of go back and forth between them. So the strategy for proving the reflexive property, for example, is super easy. All we do is we start out with a segment. We want to say that it's congruent to itself. So we just say, well, congruent means equality, and there's a property of equality, so therefore there's a property of congruence that matches it. Okay, so that's kind of our structure here. So let's set this up. The first one's pretty easy. It's almost so easy that it's hard, in a way, but we're going to do these three, and then we'll stop the video and let you add those to your homework, because you're going to prove these three in your homework as well. So this will help you with your homework. Okay, so we're going to have our two-column proof. Actually, let me move this a little bit. My whiteboard here is a little bit smaller than the one I was used to working with, so having to adjust to that. So let's do given. And we're just going to start, this is kind of weird, but we're just going to start with some segment AB, given some segment. We want to prove that AB is congruent to itself. Okay? So we're going to start with our statements and justifications. So statements on the left, justifications on the right. Okay, our two-column proof. And we're going to say, we're just starting with some segment AB. Okay? Now the next step is kind of weird, kind of tricky, but one of the things that we can do, or that we use that Euclid didn't, is what we call the ruler postulate. So the ruler postulate said that if you're measuring, if you have a segment, you can measure it, basically. You can connect it to a real number. So if I have a segment, right, something like this, you can say there's a segment, that segment will have a measurement. And let's say this is segment AB, okay? The ruler postulate says this segment has some real number measurement, and you can find that measurement and then attach it and write that measurement as AB. So this refers to the segment, this refers to its measurement. So The ruler postulate is not something that Euclid really used because he didn't really deal a whole lot with real numbers, but that's something that we have from our book. So what we're going to say is that if there's a segment AB, then it has a real number measurement that we say AB. So we'll just say AB has a real number measurement, which we write like this, right? And that's just the ruler postulate. We don't use that postulate a whole bunch, or we kind of use it without really stating it a whole bunch, but in this one proof, we don't have a lot to work with, so we're just going to call on ruler postulates to say there's this measurement, right? So now we have some measurement AB, right? What we could say is that AB is equal to AB, right? Because AB is just a number. It's just some arbitrary measurement, right? 5 centimeters, 6 inches, whatever. And we know from the reflexive property of equality that any number has to equal itself. So the reason why we can say this number equals itself is the reflexive property of equality. So I'm going to do reflexive prop, and then I'm going to do of equality. Okay? Now these things, common notions, these things were taken for granted. These things we're saying we can call upon these without having to prove them because they're pretty obvious, like everybody would accept those, right? And when we do deductive logic, we talked about using rules, definitions, postulates, laws, and things like that to build and lead to a logical conclusion. These are some of the things that we can use. These are some of the things that we want to prove because although they are kind of obvious, I think they're like a little bit less obvious or there's a few more steps if you're not familiar with congruence. So we can call on the property of equality, the reflexive property of equality, to prove that there's a reflexive property of congruence, right? So this is how we get that. Now, what we can do from here is we can say, well, if two segments are equal, right, then they have to be congruent. And how do we get that? Well, if two segments are equal to each other, then they must be congruent. That's the definition of congruent segments, right? We say two segments are congruent when their measurements are equal. So if these two measurements are equal, then these two segments, which really is the same segment, are congruent. That's just the definition of congruence. Okay, so the strategy for proving a property of congruence is to just start with a segment, switch over into like equality because we already have a property of equality, and then use definition of congruence to switch back to congruence. So it's kind of like I don't know if cheating is the right word, but it's like, hey, I need to prove this property of congruence. Well, I have a property of equality, so I'll just switch to that and then say definition of congruence says that if these two things are equal, then they're congruent. And that's kind of how you get the first property. Okay, so we're going to stop for right now. I'm going to stop the camera for a second. We're going to come back and we're going to do these two next. Okay, so come back and we'll prove this property, symmetric property of congruence and the transitive property of congruence.